So we continue with the last lecture today. We have the pleasure of having with us Jaqueline Godoy, who is not only a professor in Brazil, she's also the president of the Brazilian Mathematics Annalen. We're very proud of that. From Scotland to China. Jaqueline, the floor is yours.
Thank you very much, Leonardo, for the introduction. It's my great pleasure to be here again in Melissa. And today I will talk about some recent results in the functional differential equations, which they depend on the rate. This is the field that I work, and we try to give some motivation to work with those equations. But before to start, I'd like to thank the dedication of Professor Ludwig, that's not here, but and also for organizing this very nice conference. So this work was supported by Electronic Remote Foundation. It was developed when I was in Germany as single fellow and also campus. So I split my talk in these 4 steps. So I will start with some motivation of this field. So I will try to explain why it's interesting to work with these types of equations, the functional differential equations which they depend on the rate. Then I will talk about the work that we investigated in neutral functional differential equations which they depend on the rate. So I will explain about some model that we worked and everything that we search on these equations. And also functional differential equations which they depend on the rate. And finally, I will come with the comma open and development problem. So this is the first one that I will talk, that the linearized instability principle for differential equations. And that this other one is in collaboration with my former PhD student and my collaborator, Professor Henríquez from the Santiago de Chile, that unfortunately passed away last year. And this one is about the functional differential equations which they depend related that I will explain later. So I will start with some timeline of this field. So first, we have that these delay equations are very good to model some non-instantaneous phenomena. For example, we have several phenomena in the environment that we know that does not happen instantaneously, but there is some time in between the cause and the effect. So, for example, we saw all these years about COVID-19. And for example, when you think about to model COVID-19, it's very important to consider like the time in between the person is affected with the virus, and there is sometimes that the symptoms appear. So it's not like the person is with COVID-19 and then the symptoms appear immediately. You know that there is some time. And at this period, that's the incubation period, so it can be described as delay in this type of equation. So these equations are very important to model all those phenomena that have time in between cause and effect. And then here we have that these the works from drivers started to investigate some more complex types of delays, because we have like constant delays. But we know that most of the phenomena are not for constant delay, but these delays depend on other types of variables. So we have that Cosmos driver. He was investigating the 2 problems body in electrodynamics, and he realized that it was very important to consider delay, but not constant delay, but the delay depends on the phase. So after his works, many people started to be very interested about this specific type of delay that they dependent delay. So also we have that these 3 authors, they started to investigate about population models, and also in population models we know that the delay means the time between the birth and to enter in the maturation process. And again, depending on the population, this time that is called delay is not constant, but it depends on the stage. So here, these 3 authors, they realized that the population of a whale and seal needed exactly this time in between needed to be something that depends on the stage. So here is the model that they would like to have. Here, so it's the model, and if you see here, this is the part that appears the delay. So here this call is the delay of the equation, it's that's a function of the state. So it depends on X. So this comes with a lot of complexity for our equation, because here we have that the delay is a function which depends on the state. It's not constant. And this brings a lot of complexity to our equation, but this describes much better the phenomena depends on the model that you are working with. So, but now I will talk about this difficulties that we have behind this type of equation. So when we work with differential equations with state-dependent delays, we have several complications, and I will try to explain a little which are there. So here we have this type of state-dependent delay equation. So just to explain that the definition here. So here we have that this x under t is not the partial derivative that probably many of you are using, but here when we work with these delays, it means. So here it's you take theta here, and then you have that this is xt plus theta. So that's a function of theta. So what we have is that xt applied to theta is equal xt plus theta. So that's what that means, that symbol that you can see there. So we have here that, like, here is the state-dependent delay, you can see. So here the delay depends on the x that is stated here. And what we want is to try to investigate these types of problems. But here we have some complications, because here when you do with functional differential equations, first what we have is that the initial data, the of ordinary differential equations are functions. So here, if we start with the initial data in the continuous space, we cannot ensure in this case that the solutions are unique. So we have some problems in order to ensure the uniqueness of solution. It's not like when we have, for example, the other types of delay equation, but when we have like delay equation with state-dependent delay, it's not easy to ensure the uniqueness of solution. And here it's, for example, one very simple example about this. So here what we have like a functional differential equation with state-dependent delay. So here is the delay that we have. So it depends on the states. And what happens here? So it's very simple. And if it was constant here, so we could ensure the uniqueness of solution, because it is very mutually inclusive. But here, since we have this function that depends on the state, we have that the uniqueness is not ensured, even if we have this type of initial values here. So we have these initial values, and then we have that these two functions are both solutions of this equation. So we can also have in this situation no uniqueness. And why that happens? So this happens because if we try to derive this type of state-dependent delay in this type of equation here, that is xt means exactly that. It's in order to have this connection between the state-dependent delay and this type of equation that you can see too, it's necessary like to do this composition here. So at zero, you need to write as this composition, and in this composition appears the evaluation map. And this evaluation map, if you see here, it's like this type of function. It's not, there is no good regularity. So when we translate in this way, this function f0 will not have a good regularity because of the definition that comes with this composition and the evaluation map of this movement. So we have that the evaluation method that we saw before is in general not continuously differentiable. So because of that, we cannot ensure that all the results that are happening for this type of equation can be used the one that you saw before, like for this type of equation, we cannot translate the results here to the results with our state dependent delivery. So that's why it brings a lot of difficulties because we do not have this bridge, and then we need to develop everything for this type of state dependent delivery without using the known knowledge about the functional differential equation. So the first part we will talk about this work that we investigate about the linearized instability principle. So in order to do that, here we have about the model. So I will start with the motivation of the model. And here we would like to understand a little about exchange money and the market fluctuation. And in order to do that, we have that these three authors here, Reis and Walter, they introduced a model in order to describe the market fluctuation and the exchange rates. And here is the model that they gave in 2004. And they couldn't prove many properties concerning asymptotic behavior of the solutions, but they made a lot of conjectures in this paper. Then later in 2005 and also in 2006, Hans proved several properties concerning the solutions about periodicity and bifurcation. Then later we have that these three authors that are Kovacs and Fitz. They proved several results that were conjectured by these first three authors here. So they proved several asymptotic properties concerning the solution. Then, in 2012, Stanford was one of the first to realize that this delay needed to be not constant, as you can see here. Here, the delay is constant, but it needed to be a kind of function that depends on the state. So it needs to be something more complex. So here we have like a state-dependent delay in the model. So Stanford was one of the first to consider that, and which makes total sense. Because when you're dealing with market fluctuation, we know that the time in order to the markets react to the changes is not constant, but it will depend on other factors. So Stanford was one of the first to consider that. And then we have that Hans-Otto Walter, he improved the model, and he put here this derivative in the part that we have the delay. And when we have this thing, when we have the derivative in the part that we have the delay, we call those equations a neutral functional differential equation. So this is a neutral functional differential equation with state-dependent delay. And then Hans-Otto Walter proved several properties concerning the solution of this problem, like the distance, differentiability of the solution, linearized instability principle. However, the linearized instability principle was completely open because it was difficult to have some lower estimate from the time group that is generated from the linearization of the equation. And this difficult comes because when you do a neutral type of equation, and then you linearize this equation, you generate a same group, and when you see the spectrum of the same group, you can have infinite eigenvalues. So because of that, we have a lot of difficulty in order to have a lower estimate for the same group. So that's why the difficulty in order to deal with this model. And then we decided to investigate it exactly this and also overcome the difficulties. So I don't know what happened. Okay, I think it's now. So here we have the problem. So this is the problem that we studied. So here is neutral because we have the derivative in the part that appears delayed. And this is a state-dependent delay because the function of the delay depends on the states. Then the first step that we had was to rewrite this equation in an abstract form in order to include not only this model but the other models too. So we also included here some engineer problems in this model. And then we would like to prove this more general type of abstract equation. So we prove it for this equation here. So we needed to rewrite our problem in this way. And also, of course, we needed that our G satisfies some abstract conditions that makes total sense in our statistical model. And then, for example, for our model, even though it appears and seems to be a lot of conditions, in our model, everything works very well. So we have here, so in order to rewrite this equation here in the abstract form, we need again to deal with the evaluation maps. But here we need to work not with only the evaluation method, because as you saw, it's not possible to translate good conditions to our abstract problem. We decided here to work with the restriction of the evaluation method. So here is the evaluation method, and then we work with this restriction that the evaluation method that's here is restricted in C1. And then using that, the conditions improve in our case. So then if we define our G in the abstract equation as all this composition here, where here is the restriction of the evaluation map, and D is the projection concerning the second factor, here is the projection concerning the first factor. Is that possible to have a link between our model and this abstract equation? So we could have here just the tutorial again. So we have a relation between this type here and this other type here. So we could have this relation. Then using this definition here for our G, we could prove that many conditions about the G is satisfied in order to prove our results. So let's see the condition. So the first one is about the continuity of our function. So G needs to be a continuous function. The second one is a little strong condition, but in our case, no problem at all. Here, what we have is something like we can disconsider the case that the delay in the neutral part vanish. And what that means? So you can see here what we have. So here we have a minus h minus delta, and then here if we have that it is f1 is equal f2, but then here they change, like one goes here, the other goes here. It doesn't matter what happens here, we can disconsider that because our G evaluated in P1 will be equal in G evaluated in P2. So which is important is only what happens here in this part. So using that condition in our case is good because usually when you do that, you avoid, for example, some model that particle shock. But in our case, we do not have this problem. Since we are dealing with a market fluctuation model, and also we are dealing with an linear problem. But it could be not good, for example, we are dealing with something that you have some shocks between the particles. So in that case would be not good. But it was very important this condition in order to prove our results. And in our model, it is satisfied, so it's no problem. So here also we have some types of Lipschitz conditions, so types of local estimates that we have. And then here, this one is a very, very important condition that we have in order to be able to construct our manual. So here we ensure this linear extension of our derivative. So here we have that the restriction G1 of G to this open subset here. Also, these we have this case that's continuously differentiable. What we have is that every derivative that is defined here can be extended in order to have this frequency. So this will be very important in order to define our method. So this is the linear extension of the derivative. And these conditions appear in many other works from delay differential equations, which they dependent delay. So, and also they call it this type of condition as almost perfect differentiability. So what we have is that from that condition, we can prove that this set here that we will call like xp2 given by this one here. So all functions that are in this state such that satisfy this type of equation, that's our equation that we had before. If it's not entity, we have that if we have the structure of a manifold. So we have that the submanifold of a balanced state. So using that, it will be very important to us in order to have this structure of manifold. So here also we have this other type of conditions that again with some estimates that will be important for calculation the technical. Also give about upper semi-continuity, but only to mention that even that seems to be a lot of conditions, all of that are okay in our model. So we fix all those conditions here. And then is the last one that we produced here. So what we have is that our G in the abstract form, it satisfies all those equations, all those conditions like the continuity, also the liquids, and also the most important liquid tree, and the other estimates as we saw before. So then here we have that the solution of this problem we will understand as a function that's continuous, differentiable, and will be defined this way here. Will be a solution if, of course, if it satisfies our equation here, and also if we have that it belongs to this open subset here, that is a subset of C times C naught. So that what we first have, if you remember, we have that xg2 is it has the structure of a manifold. However, we do not, we cannot be sure that you cannot ensure that if you are there, you continue there, like if you apply. You cannot ensure that invariance. So here, in order to ensure that invariance, and that will be very important to us, this invariance, we need to define a new subset that is given by this xp2 star, that is the closest subset of the neighbor. And Hanzoko also proved that this closest subset is invariant, which means that if we start here, so your solution will continue there. So you have that your solution continue here. So we need that because the strategy that we will use here will be the invariance of the form. And in order to do that, we need to ensure that our solution continues in some subset, not goes out, and we do not lose some property. So here, as I mentioned before, our goal is to prove that the linearized instability of the solutions of this problem, and the strategy that we will use will be the invariance of the form. So in order to do that, we have again some abstract conditions here that we also call all those conditions will be satisfied in our specific case. And this first one would be one of the most difficult that we have, because here you can see what that means is that you can divide one space in a part-based table, and also in a direct sum of the stable part and the unstable part. But then here, what happens is that when we make the linearization, what will happen with the semi-group that is generated is that, as I mentioned, that's okay. You have this upper bound, that's okay, but this lower bound, it's not easy in the case of the neutral equation. And here we had a lot of difficulties in order to overcome that. But we could see many examples in our case that we could fix this, but it happened because our equation had some perturbations that we could work on that. But sometimes it's difficult to have these in all types of neutral equations. So what we have here, so we have the decomposition of the space, and here we have this in the unstable part, the estimate, and the estimate of the same group that appears from the linearization of the unstable part. Also here, we have this property. This property it comes very quickly to us because before Professor talked about the proof the existence of same flow. And then here we have that property like directly. So we have that our P here is a same flow, and the same flow satisfies these three conditions that is from the definition of same flow. And then here is one of the most important part, that's the difference between our solution and this linearization. So we will call this like this R, that's this function here. And the what we have is the following. So we assume that there is this 2, 1 bigger than 0, such that for every epsilon, there is this delta, such that we have the inequality here for some time T1. So we have this estimate, which means that the solution, the nonlinear solution, is very close to the linearization. Okay, so we have that happen here with our difference. So and also here we have this constant k that appears, and in order to avoid to use a lot of variables here, we will use like an equivalent norm. And in order to do that, we will consider that our case is equal 1. So here we will change for this equivalent norm here, and then we will assume that our case is equal 1 in order to avoid to be carried all the time in variables. And then also here we have the definition that this norm will be the maximum between the unstable part and the stable part. And then here's the definition of our cone. So we have for C here, we have that these are the elements in our space. As we saw, we could write it in this direct sum. And then we have the unstable part and the stable part. And what we have that the unstable part is bigger or equal this C times here the element. So using that. Interesting. Okay. So now what we have is the following. So here we have our invariance of the cone and the extension that means the following. So here we have this Q. Also we will assume that all those conditions that we had before are satisfied. And then what we have is the following. So if we start in the cone and they place in the ball, what will happen is that when we apply the T1 map, you continue in the cone here. So here is the cone. So the cone is invariant. And more than that, we have the expansion of the unstable part. So here is the new unstable part that's given here. And this term here is bigger or equal to this Q. And this other one, but this Q is bigger than 1. So we have this extension of the. So let's see how it looks like with the tools. Only some ideas. So here we have this epsilon that's given by this minimum here between these two things. And we will take our delta as the one that satisfies the condition A3 for the norm 0 that we introduced. So what we have? So we know that the norm of the projection is 1. And then applying this projection for the unstable part of our T1 map, we have from the definition, if you remember this R, it was the difference between P and also this F. So using the definition, we have this equality here, now only passing this projection here, so we have that. And now we use here the estimate that we have. So triangular inequality to the other side, and then here the lower estimate for the same group. So we have that. And then here we use the function A3 that we have that is more equal to actual. So since you are in the other side, so you have this. And then here also working with the estimate that we have here concerning the thing that the cone, we have this up here this thing. So also we have this estimate. So now if you apply the projection for the stable parts, we have an analog that we had before. Again, using the definition, we have that then we can only pass here this projection, and using the estimate, so here the estimate for the stable part, so we have here for our semi-group that appears in our assumption A3, and also the A1, sorry, and this one is for A3. And then using the triangular inequality, we have that. And then here, using the property concerning the projection, we have this other inequality here. So we have these two inequalities. And then what happens here? So we have this T1 is the maximum of the projection for the stable part. And then here the projection of the unstable part. Then, as we saw before, this one here is smaller or equal this quantity, so we have that, and this we only keep this way. So what would happen here? We have two possibilities. Or maximum is this one here, or the maximum is the other one here. So let's assume that the maximum is that one. So in that case, since this is the maximum and this is smaller or equal the maximum, so we will have this inequality here. And here, again, since you have that C is more or equal 1, we have this other inequality here. So what we prove is that here it satisfies the condition of the cone. So the T1 max belongs to the cone. So here we have the invariance of the cone for this case when the maximum is this quantity here. So now we need to see what happens in the other case. So to the other case here, we will have this inequality. And now, using the choice of epsilon that we had before, and also the estimate that we had. So here, we are using also this estimate. We start to use the estimate that we showed in the first part of the proof. And here, we have using here the fact that let's see here. B, you know that is smaller or equal to maximum, and we are assuming this is the maximum. Also, this is bigger or equal that. So we are using this thing here and multiply both sides by C. So you not change the inequality because C is bigger than 0. And then here we only sum and subtracting things, so that's why that's equal. And then here using the choice of epsilon, and then we have this inequality that appears here. And now using our first estimate, we have this other impact. So again, if you see here, what we have that the T1 max belongs to the cone. So we have the invariance of cone. But here we need to prove the invariance and also the expansion of the stable cone. So for the expansion, it's also we apply here the projection for the unstable part of the T1 max, and then using this that we had before. So we have the estimate, and now using the property that X belongs to the cone. So we have this inequality that appears here. And now using the definition of epsilon, the choice that we have that. And this only make the calculation. We have that, and this is the Q that we had in our theorem that we defined before. So now here what we have exactly is that we have the expansion here of the unstable part. So we proved this thing about the invariance of the cone and also the expansion of the cone related to the unstable part. And it will be very important in our case in order to prove our main results. We proved this lemma in a more general sense, but we can translate everything into our specific case of our model, and we have that all conditions will be satisfied for this case. So now we need one more condition in order to prove our linearized instability principle. And this other condition will be very similar to the one that we cut in the beginning, the one that I told that it would be very important to the D3, because but there you have the linear extension of the first derivative. And then here what will happen is that we will also incur this linear extension but related to the second derivative. And it will be important again because of the manifold structure. So what we have here is that B here has a continuous extension now of the second derivative, or second derivative, sorry, to be 3 times 3. And then using this hypothesis, we can construct our manifold. Because if you remember before, what we have, we first have this, for the other condition, we had that this one that we defined before was a manifold. And then we defined the closest subset here of this manifold that it is invariant. But we do not know about the structure of a manifold here. So here, but if we have this M3 that is this intersection here, we can have using this condition that we have this structure again of the manifold because of this intersection with C3. So in using that, we have that this M3 the submanifold of C3. So now, using all those instructions, we can prove our result. So the main idea is the following. So we start in the ball, so with the solution, and then we apply the T1 method, and we see if the solution is escaped from the ball. If the solution is escaped from the ball, we finish because this is stable. But if it does not escape from the ball, we need to apply again the other T1 method. And we need to continue on that. And we know that it continues in the cone, and also we have that it's continued in that it starts in the manifold, and if you see here the definition of the manifold is this. So we know that if you apply the T1 method, you don't know if it continues in the manifold, but you know that it continues in that fact here because it's invariant. So we can continue with this process to provide a contradiction, because if you continue applying the T1 method, since you have the extension of the unstable part, there needs to be some moment that your solution escapes from the ball. Otherwise, you would have a contradiction. So that's the main idea behind of the proof of the linearized instability. So here is this principle that so what that means. As I mentioned before, you have that for f, and there is some moment that your solution will escape from the ball, and then we have here the stability. So this is about the first problem that I worked at, and now I will give some ideas about the second problem, since I have no longer time, but only to give some ideas about this second one. So for the first one, just to mention that there are many open problems in the area, the field. For example, we are now thinking about other types of instability, because we have a linearized instability principle, but for example, exponential instability. We are seeing if it's possible to have some conditions there in order to ensure these types of problems. So we are now trying to investigate these types of problems to the other type of equation. Also about periodicity, bifurcation, all of these are still open problems for that equation. So here now, in this other work, we also work with a state-dependent delay. And here you try only to mention some ideas, but you're not go deeper as I went to the other one, only to give some ideas behind. So in this one here, we worked with this type of problem here. So here we have this type of state-dependent delay, and here is the initial condition, as I mentioned before, this is a function, so it's the same definition that appears here, but our speed is equal to 0. So we have a function, that's our initial condition. And here, one of the main problems that we had is the following. When we deal with this type of problem, we could have many difficulties to overcome that, because if you see, we have a decomposition. This here means, I mean, for here, so it will be easier to see. But if you see here, we have this t, xt, that it applies to some theta, and then it's like x theta plus t xt. And here what happens, if you see, If your solution is continuous, okay, no problem. But if you like that your solution is not a continuous function, then we can have a lot of problems. Why that? Because even if you have that this is continuous, if, for example, you ask that this one is regulated function, that means the lateral limits exist. So if you do that composition, you do not know what will you have. Okay, suppose that we have here the regulated function again, but then you have a composition of a regulated with a regulated that you don't know that it's a regulated or not function. So that's why a lot of problems when you deal with this type of problem for regulated function. But here we worked with this type of function, the regulated one, and what we use it in order to be able to do that, we use it such a type of monotonicity for this function. And using some properties, we could define well this type of composition here in order to have this type of more general type of function. Because we wanted to deal with a more general type, and we didn't know how to do that. And that was the idea that we had. And also we made some connection between state-dependent delay and time-dependent delay. When we have here this code, not depends on t and the x of t, but only for t. And then we made some correspondence in that case, putting, of course, some conditions here in this code. So doing that, we also could translate some results from one side to the other. And then we proved several results in that direction. It was difficult because there are many difficulties when you deal with a regulated function. But we could overcome that because there is a Argyle theorem for regulated functions that we could apply in that case. And then we could prove some results about the distance and so on. Also, here we had a lot of other difficulties because here, if you see, we have unbounded delays. Here, it's bounded, so we have this compact interval, but here we have unbounded delays, which means that if you see, if you are, for example, the continuous function set, you no longer can ensure that the band space, because here we have that situation. Also, the same happens with the regulated function. But then we needed to define a new phase space in order to be able to investigate these types of equations and to define appropriate spaces in order to work with this type of equation. So there were the many difficulties behind this type of problem, but there are several motivations to investigate these types. And also we could apply these results for this equation here. So we could do for this equation on the hips, and for with here using the state-dependent delay. So it was nice because we could work with this partial fraction equation using state-dependent delay. And we are seeing that it is very, very nice to have both combinations of partial differential equations with delays. It was very well investigated before. But with the state-dependent delay, it also means to be very nice to depend on the situation, on the phenomena that you are working to model. So these were about these two problems that we investigated using state-dependent delay. But there are several open problems in that field that could be done in that direction. Because of this state-dependent delay, few people are working on that because of these difficulties that you saw, it's not easy to deal with that because you lost a lot of regularity of your function, of your solution, and because of that, it's hard to deal with it. But it's very nice to introduce in your model this type of state-dependent delay, because you can have a better description of the phenomena that you'd like to investigate. The same, for example, happens for COVID-19, because we know that this period of incubation is not the same for everybody. Sometimes it could take longer, or it could take shorter, and you have this variable delay brings more reality to our description of the phenomenon. And also here, we use that for the market fluctuation, but also is that possible to use that in many other types of problems. And there is one very recent work that's about cancer cells population model. And it uses exactly this state-dependent delay and with a partial differentiation. And it's a very interesting model because we know again that the reproduction of the cancer cells are not instantaneously, and it depends on the stage of your cancer. So that's why it would be very important to consider this type of state-dependent delay. So there are several models that can be investigated in their direction. And also this part about regulated functions, solutions of discontinuous solutions for this type of problem are still completely open, also because the difficulty when we have these compositions here. So it's also very nice to think about those types of problems. And also, just to finish, we have